Hello, everyone. Hope you're doing well. I'm gonna ask you to wait a bit until Mr. Ben Boudiaf came again. He's coming in any second. Sorry for the
I'm
delay.
back, Osama.
Okay, so we'll start. Hi, everyone, and welcome. I'm Osama Ben Dahman, the moderator of this session. Now that we've reached the sixth webinar, with the title of Introduction to Oilfield Geomechanics presented by Mr. Merwan Ben Boudiaf. Mr. Ben Boudiaf is a petroleum engineer with 4 years of experience within Baker Hughes Reservoir Technical Services Department. He specialized in geomechanical modeling, wellbore stability analysis, MicroFrac pre-job design, and post-job analysis. He worked in several projects in North Africa and the Middle East, and he's currently leading Reservoir Technical Services activity for Algeria, Tunisia, and Libya. I would like to remind you that the session is being recorded and will be shared on YouTube. I would also like you to fill the attendance sheet that we will share in the chat box. If anyone has any question, please drop it in the chat box. Mr. Ben Boudiaf will answer it at the end of the session. Please keep your mics off. Mr. Ben Boudiaf, the mic is yours. Feel free to share your screen.
Thank you, Osama. Thank you. So, hello, everyone, and thank you as well for attending today's presentation. So, this presentation is a general overview of all what is related to geomechanics, what is a geomechanical model, and how to construct it, and all the benefits related to this discipline. So I'm just sharing my screen, and I would just like for you to, Osama, to confirm that I'm audible and that the screen is.
Yes, we're seeing it.
Thank you.
You're welcome.
Okay. So let's start directly. So with the topics, as my attendance of this presentation are Boumerdes students. So I would like first to make a brief introduction of Baker Hughes company and also Baker Hughes Reservoir Technical Services department. So our students will have better visibility on all the activity of our company in Algeria and over the world. Then we will go for Baker Hughes Geomechanics Services. So just a general overview of what we're proposing in general. Then we'll enter more into technical, and we will go through the steps of building a geomechanical model, what we need to do and all the steps to follow. Then we'll finish with some of the main applications of so building a geomechanical model that benefits the oil and gas industry. So let's start with the introduction of Baker Hughes company. So Baker Hughes is mainly composed of 4 product companies, as what we call them. So Baker Hughes is first of its kind, what we call a full stream service companies. It means we are providing services at all levels of the oil and gas industry, the upstream, midstream, and also downstream. So the first product company, so we have our Reservoir Technical Services department. It's called Oilfield Services. So it's more or less so compounds all the well formation evaluation, drilling, and also fracking production services that we are providing to our customers. We have also another products company called Oilfield Equipment. So the main specialty are the flexible pipe system, surface pressure control like the wellheads and etc. Drilling equipment, and also some kind of connectors. We are also specializing in what we call non-metallic components for the oil and gas industry. The next one is called Turbo Machinery and Process Solutions, or TPS. So we are here is really a very broad portfolio of that. So they are supporting all the onshore, offshore production, pipeline system. So mainly they are acting like along all the midstream and downstream industry. And the last one is digital solutions. So they're providing so all measurement sensing services, control solutions, also all kind of inspection technologies. We have also what we call BHG Digital that are developing software solution not only for the oil and gas solution, not only for the oil and gas industry, but also for other types of applications. So let's go directly to Reservoir Technical Services Group. So, we are a group providing reservoir consultancy services, and we are operating along all the phases of the development of a field, from the exploration phase with all reservoir characterization and field development plannings, towards the rejuvenation of oil field, and also the commissioning of the reservoirs. So so this group is providing different type of services that are fit to the needs of different customers at different levels. So it's going from the geology and all the geophysical support towards the drilling optimization, completion, and also the production optimization. And also more recently, with the booming of all CCUS related applications, we also providing all solutions that are related to carbon management for the storage. So let's start with geomechanics. So where and why do we need geomechanics? So let's first look at the drilling phase of a well. So during drilling, we can observe different type of issues or challenges that are related to the geodynamics of the earth, to the pore pressure, and that can be solved by the discipline called geomechanics. So here we have some, like during drilling, we have overpressure issues, we have lost circulations during drilling, generally wellbore instabilities. We have the challenge of drilling through naturally fractured reservoirs, which is very common challenge in our country, Algeria. We have also challenge related to sand production for the depleted fields. And also for some regions, we have casing deformation, so due to the high underground stresses. So all those type of problems can be solved by geomechanics, in fact. So reservoir geomechanics, so this is just a general definition, is defined as a branch of science that integrates and combines several other sciences like geology, rock mechanics, petroleum engineering, in order to solve geomechanical problems that arise during the lifetime cycle of a well. So you can see that geomechanics applications are starting really from the very beginning of the development. Fault risks means all the fault slippage related risks for the wellbore stability for the drilling, and it's following until the very end of exploitation of hydrocarbons, with all the compaction, subsidence, and also stimulation related applications. So here is a diagram of different geomechanics applications that's dependent on the complexity, and also on the x-axis dependent on the maturity of the field. So at the very beginning, so we have the very simple geomechanics called the stresses estimation, SH min, SH max. This has direct applications into drilling, deviated wells, the mud weight optimization, and all wellbore stability studies. These are 1D applications. Then we are going to here, so to all pore pressure related. So this is not really 1D and not really 3D. So it's between the two, just as sending analysis. And we can go to what very complex applications like the casing deformation, fault seal, or analysis related to fractured reservoir that we will see later, and also compaction subsidence. So now we'll go through the steps for building a geomechanical model. So first, what is a geomechanical model? So description of a geomechanical model involves detailed knowledge of the following. First of all, we need to agree that we have three stresses operating on the underground. So we have two horizontal stresses, noted SH max and SH min. So one is the maximum and one is the minimum. And we have one vertical stresses called the SV. So those horizontal stresses have a different orientation depending on where you are located on the planet, or dependent on any fault or geological structure that is proximate to your well. The second parameter is their magnitude, so the magnitude of the three different stresses. Then we have the pore pressure. So this is the energy that is contained inside the pores and inside the void of the rocks. And at the last one is the rock mechanical properties. So the most, like the one that is mostly calculated and useful is the UCS, called unconfined compressive strength of the rock. We have also some elastic properties such as the Young modulus, Poisson's ratio, and internal friction coefficient. In order to construct a proper geomechanical model for different types of applications, we have also other considerations that we are including into the construction of the model, such as detailed analysis of mud chemistry for drilling, also weak bedding planes for all wellbore stability related issues, presence of natural fractures, that is a critical parameter for if we are doing any hydraulic fracturing related study. And also for some regions, we need to take into consideration the thermal effects that also are dependent on their gravity, can have a significant influence on the stress magnitudes. So first, in order to construct a geomechanical model, so we need a lot of data. So I'm speaking more more particularly to students that maybe want to go for like geomechanics as their final thesis subject for their master. So in order to construct geomechanical models, you have different types of data that you need to gather in order to arrive to a good calibration for your model. So for example, for the vertical stress, you need all the density logs for the well, or maybe pseudo density from acoustic that is calculated. For pore pressure, you need some direct measurements, or also some acoustic and seismic data in order to construct the curve. For rock strength, you need the lab measurements and also acoustic that will help you to construct the log-based profile for example, for the UCS. For orientation, you need the image logs and etc. So we'll go through that in detail. So here's the workflow. So for every 1D geomechanical model, this is the preferred workflow you can go through. So for example, first of all, you start with drilling event analysis. So either you are doing wellbore stability study or hydraulic fracking study, sanding. So it's always worth it to look at what happened during drilling. So you will always find some very useful events that will help you at the end to calibrate your geomechanical model. Then after reviewing all the drilling events analysis, we go to vertical stress magnitude, then pore pressure construction, least principal stress, which is also the minimum horizontal stress, rock strength and all the rock properties, then the maximum horizontal stress orientation. Then at the before the last step, we are calculating the maximum horizontal stress magnitude. That is calculated based on the values of all what we have calculated before. Then at the very end, we are doing a model verification against what we can see, for example, drilling events. So the final geomechanical model that you are constructing will need to explain what happened during drilling first. So this will help you to calibrate your model. Then also you can also calibrate it with different type of failures in the borehole, such as the cavings or maybe what we can see on caliper log, for example. So every slide will contain like the steps that we are following. So I will show some examples. So first thing, what we are doing is the drilling events analysis. Usually we are presenting it through this type of diagram. So you can see on the x-axis, you have the dates, like the advancement of drilling through time. On the y-axis on your left, you have the measured depth that is also represented by this blue line here. On the y-axis on the right side, you have the static mud weight that was used for drilling, and this is represented by this red curve here. And then what we are doing, we are plotting different events. For example, in red is tight hole, stack pipe, partial losses, inflows, etc. So we are plotting them at their respective depths here. And we are putting some comments like in order to, so by putting like this, so what we are doing, you are correlating those drilling events to certain type of formations. Here I have put as an example a very classic lithostratigraphic column in Algeria, for example, in the region of Hassi Masoud. So for example, you can see, I can just analyze for you like briefly, you can see that we have high concentration, for example, of tight holes here at the top of this Dogger formation. So this can help you after that. When you are constructing the model, you can see that the model is replicating some kind of failures towards this formation. So those events are explained by your model. So this is how you calibrate your model. Then also you can look at the caliper curve. So this is mainly the mean diameter of your borehole. Even if you don't have drilling events, you can also have a look at this. All those enlargements are signs of borehole instability that you will need to reproduce with your geomechanical model in order to validate it. Then second step is the overburden stress. So basically the overburden stress is the weight of all the overburden formations that we have. This is why we are using the bulk density log to calculate it. So whenever it is available. Otherwise, what we are doing, we are using the acoustic data or sonic data like for different denominations in order to calculate what we call a pseudo density curve. This is one of the generic equations that we can use in order to calculate the density from the acoustic slowness here with the two coefficients exponents, 0.23 for A and for B, for example. We need to vary a little bit if we are going into shale and sand or if you are working in limestone. So this is an example. So this is different density curves that we are plotting together along well. And where we don't have the density, so we are basically generating a trend line with some equations here. You can see the A, B coefficients. So this is an exponential trend line that we can use to fill the voids. For example, mostly so for shallow formations, we never have any density logs. So usually what we are doing, we are just extrapolating this trend line, and we are taking it as average value for the calculation of the overburden stress. Then now the pore pressure. So basically we are estimating from logs and also from direct measurements such as DST or some wireline operations like MDT or RCI. So from like logs, basic principle is what? So we are taking the curves that can that have a relationship with the porosity of the formations. So what the theory says is that so with the depth we have a constant compaction of the sediments. So what Eaton has supposed at the beginning is that if we have a constant compaction of the sediments along the depth, it means that we should have a constant reduction in the porosity of the formations. This is what, so for example, in some regions where you don't have any anomalies in pore pressure, you will see, like if you are plotting all the porosity curves from the surface to the bottom, you will see kind of very constant reduction in pore pressure with some local variations for sure. So what Eaton said is that if, for example, you have some higher porosity at a depth, it means that this porosity could sustain this this compaction because it has more energy. It means that it has overpressure. So what we do, so we are putting what we call a compaction trend line like this, for example, for velocity or density or resistivity curves, and all the variations. If these variations translates into higher porosity, it means this higher porosity is due to an overpressure relatively to the normal hydrostatic pressure. And this is how we are constructing kind of pore pressure profile that needs also to be calibrated or verified against the drilling experience, and whenever it's possible against the direct measurements such as DST or MDT, as I mentioned before. So now we're going to minimum horizontal stress estimation. Usually the minimum horizontal stress is estimated from leak-off tests or extended leak-off tests or mini-frac tests. So mainly those are translated into the same kind of operations with minor variations. Basically, those tests consist of pressurizing the wellbore. So you are closing the well or part of the open hole, and you are starting to increase the pressure in that interval. So you are increasing the pressure gradually until you are observing this like deviation from the linear. It's what we call the leak-off point. It means that we are starting to initiate like small fractures that are absorbing the liquid inside the borehole. This is so this we call leak-off pressure. Then when you are increasing pressure at a certain point, you are breaking the formation. So here you didn't yet break, you're just initiating small fractures. It is a full breakdown of formation. So this is formation breakdown pressure. You are pumping a lot more, so few more barrels in order to propagate this fracture the most far from the borehole. Then stopping the pumps, you are observing this natural decline. And so from the analysis of this decline, we can get the fracture closure pressure, which is mainly like the best estimation of minimum horizontal stress that we can have. Usually this value can be inferred from mini-frac or micro-frac tests. For leak-off tests, usually they are not going so far and they are stopping at the LOP. So some specialists, so they can consider this leak-off pressure as a higher bound of minimum horizontal stress. So we can use it for calibration, but we should say that the minimum horizontal stress should be slightly lower than the LOP point. As you can see here in the diagram, the fracture closure pressure should be always lower than the leak-off pressure. Then rock strength. So the next parameter we need to estimate is the rock strength. So first of all, we need to look at the course that we can have, either in the well they are studying, or maybe you can ask to have access to data from other offset wells where you have some mechanical testings on course that have been performed that will help you to construct some equations for your rock mechanical properties. So we have mostly, like for rock strength, we have two types of tests. We have first the uniaxial, triaxial tests that are performed on plugs. Those plugs are taken from the main core, and they are pretty small. So that's they are 1 inch in diameter and 2 inches in height. And observing the failure here and at the pressure at which the failure occurred and give us direct estimate of the rock strength and also of the rock elastic properties such as the Young modulus and the Poisson's ratio. So this is called the destructive test. We have also non-destructive tests such as what we can see on the left. It's called a scratch test. So basically, so it's a kind of very small knife that is scratching the core from top to bottom, and it's measuring directly the UCS of the formation. You can have the continuous profile instead of having only 1 point for plug estimate here. So once you have your core data and you have all the results, so you can construct your equations, and then from the logs, for example, from sonic log or density or porosity, so you will have to choose and to make some tests in order to validate it. You can construct some equations to calculate your mechanical properties. For example, here you have some, okay, here you have the gamma ray, caliper, this is a resistivity, and all the acoustic logs. Here you have the uniaxial compressive strength. So the black curve is so generated from sonic log. You have this blue curve here, it's the scratch test, and also you have the red dots here that are the test like mechanical tests performed on plugs. Same for internal friction coefficient, Young modulus, and Poisson's ratio, and also the tensile strength of the rock. So once you have, you have some kind of good calibration, such as here. So you can see that the curve is matching with around 80 to 90% of the dots. So you can say that you have a good calibration for your model. Okay. So before to go to the next parameter, just a brief moment of theory. So when you are drilling a well, so vertical, so we'll take as example here a vertical well. So what is happening when you are creating this deformation inside the earth crust? So you have your principal stresses that are SH max here as principal here as SH min. So around the borehole, you will have creation of new stresses, you can say, that are directly related to the geometry of this hole. So you have one radius stress that is also related to the pressure from the drilling mud, and you have the tangential stress here in fact as sigma theta, that is so as you can see is acting at the borehole wall, and so its magnitude will differ from the azimuth you are seeing. So if you are staying in front of SH min of or SH max, the magnitude of this tangential stress will vary, and we'll see that in the next slide. So here you have here the red curve here is the variation of this tangential stress along the borehole wall on half circle here, so on 180 degrees. So you can see that this tangential stress is reaching a maximum. So at certain point, and this point is corresponding to the azimuth of SH min, and it's going like a sinusoid, and its minimum is at 90 degrees from SH min, so it's at the direction of SH max. So analyzing this curve, what we are deducing is that at the direction of SH min, the borehole wall is under compression. And at the direction of SH max, you can see here, it can go under zero here. So it means that at the direction of SH max, the borehole wall is subject to tensile forces. So what is happening when those forces are exceeding the strength of the rock? So for example, at SH min, when it's exceeding the resistance of the rock to the compression, so we have some failures that can appear on image logs and are called breakouts. You can, as seen here, this very dark bands here. And at the direction of SH max, when the magnitude of this minimum deflection of tangential stress is going under the tensile strength of the rock, you have the appearance of those what we call drilling-induced tensile fractures. So the appearance of those features will seriously help us for the next two parameters of the geomechanical model, that are the orientation of stresses and the magnitude of the maximum horizontal stress. So by detecting those breakouts, for example, it's here, it's an example for breakouts only. By detecting those breakouts, we can directly get the orientation of at least one of the horizontal stresses. For this case, it's the SH min. And from SH min, we can directly infer the orientation of SH max. For example, if orientation of breakouts is 23 degrees, you just have to add 90 degrees to it, and you have the orientation of your SH max. So usually, like the convention says that we present usually the orientation of SH max for all the wells. So to be aligned like with all conventions. Here, another example with the presence of breakouts and tensile cracks here. Here you can see just like cross-sectional area of acoustic image log that is showing those breakouts, and with a certain width here that can be calculated. And this width will be a parameter for the generation of SH max magnitude. So for the magnitude, so what we are using, so we are using stability equations from the Moore-Coulomb criteria, and using those equations, we can basically construct this kind of what we call stress polygon. So every limit of this polygon has so it's related to one of equations here, as you can see, and this one is limited by the SH max to SH min ratios here. So here what you have SH min on the x-axis, and you have SH max on the y-axis. So basically having SH min and having all the rock properties, you can directly get your SH max value. And another benefit of this stress polygon is that we can understand which kind of stress regime we are in. So for information, we have three different type of stress regime, what we call normal faulting, strike slip, and also reverse faulting. So I'll just show you one example here. So for example, here we have breakouts on image that have been picked. And those squares, from those squares, we are calculating the average width of those breakouts. So basically we are plotting this. So we have the SH min, And we have the width of breakout, which from which we can construct those red abacus here. So for the UCS, so directly having the SH mean and having the UCS, you can directly know your SH max here. So usually we are presented as a range, not as a solid value, because it varies a little bit. So from one depth to the other. So here you can see that it's going into this this triangle SS. So it means that the stress regime that is occurring in this region is strike slip stress regime, which is like the most common one that we can find in Algeria, in the Algerian desert. So the last step is the model calibration. So basically, so what we are doing here, we are plotting what we have seen on the image logs. For example, here you can see on those blue dots here are all the breakouts that have been identified by the image, and the red ones are the ones that have been generated by the model. So for example, you can see here that we have coverage only for this lower part. You can see that we are basically identifying breakouts at the same depths as modeled by the model, with some uncertainties, as you can see here, that are mainly caused by the model, so the model uncertainty. You can also, in order to be sure that you are okay with the model, to look at the caliper. For example, at this lower depth here, you can see that the caliper is very enlarged here. Even if we didn't see any breakout on the image, it means that in this area, the borehole was the borehole wall quality was not good. So maybe there was some washouts or something that so prevent us from picking the breakouts from the image log. But you can see that we have enlargements. It means that the model was true here by replicating some failures in red. You can also have a look at the drilling events, for example, tight holes, reaming, etc. And also, so you can relate those events to the failures that are happening at certain depths. So you can explain those drilling events by the failures that are happening. So let's go briefly for some applications of geomechanics. So first of all is the wellbore stability. So basically, we are using three parameters: the pore pressure, the fracture gradient, and also the collapse pressure, which is directly related to the breakout occurrence within the hole. Those three parameters are used to determine the mud weight ranges in drilling, and also to optimize trajectories for deviated or horizontal drilling, and also like the casing set points. Second application of a geomechanical model is the sand production prediction. So we can quantify the sand production. With the volume estimations, either in open hole, cased hole. So we can optimize the well trajectories, the perforations. So some advanced applications. So we can go for inflow models, transport and erosion models. And so from geomechanical, we can construct a full sand management planning. So to help into producing from unconsolidated formations. Also, you can analyze the stresses that are occurring on the casing, and you can analyze some kind of experienced the casing deformations. So here at the left, it's example of multilateral well, and at the right you can see example of casing bending here due to high stresses. So this is case that you can find a lot in North Africa and Middle East, especially due to presence of faults that are perturbating the stresses and causing these higher stresses on the casings. So from this analysis, we can optimize the casing design with the optimum weight and all the yield strengths that are all related. Another application is fracture permeability. So I will not go through that too much, so because it would need an entire presentation for it. But you may know that for the tight and naturally fractured reservoirs, the fact that a natural fracture is open or no is directly related to the geomechanical model or the stresses that are present in the region. So using this, so what you can do, so by having a full discrete fracture network such as here, you can just inject your geomechanical model and see where you have higher density of permeable fractures that will be the main contributors to the production of hydrocarbons. So this helps directly to, for example, in the implementation of wells, positioning of horizontal drains, etc. Also, so one application, so we're doing, so it's the fault slip analysis here. So you can identify, for example, at which level of depletion of a field, or inversely, at which level of injection, because in some fields we are doing like intensive injection of water or of gas. So this influences the pore pressure locally, and then influences directly the distribution of stresses in the field. So this may cause pre-existing faults to reactivate and to slip, which can be like very risky for the exploitation in the region. So you can do a time-lapse analysis and identify what are the conditions that will lead to this slippage and how to avoid it. One very famous as well application of geomechanics is all related to the hydraulic fracking. So you can go from like a single well to full 3D multiphysics approach for example, for all shale gas and tight oil, tight gas applications. And so one also time-lapse analysis that is that's possible is the compaction and subsidence analysis. So with the depletion of the fields, so you have what we call the compaction of those sediments that can also cause subsidence, and so may cause some damages to surface facilities, towns, etc. So this kind of analysis can be done as well for very old and depleted fields. So this is the end of presentation. So it took longer than expected. My apologies for that. So once we have seen that like reservoir geomechanics is a core discipline that really treats with the most facets of the oil and gas industry, like from the exploration, the drilling, the production phase here. So so thank you for listening, and so if you have any questions, it's more than welcome.
Thank you so much, Mr. Ben Boudiaf, for this amazing presentation. I hope everyone enjoyed it and everyone got as much as possible informations. So I think there are some questions in the chat box, if you want me to read them for you.
Okay.
Okay. Abdelkader Bakouri asking, what do we take into consideration when estimating the parameters in case of a naturally fractured formation?
Very nice question. So in case we have a naturally fractured formation, so we are going first through the normal workflow in order to estimate all of this. So the tricky part will be really the least principal stress estimation. This will be the most challenging parameter to estimate, because least principal stress, as I mentioned, so I will just go to the slide. So basically you are creating a fracture and propagating through this fracture in order to get those parameters. But when you are in a naturally fractured formation, the most likely you will open pre-existing fractures. So this would not give you the same values, and you may underestimate your minimum horizontal stress. So usually what we are doing a sensitivity analysis, and we can go even to fracture permeability analysis in order to understand the full picture of this. Then we can deliver like a minimum horizontal stress estimation with a range of uncertainty. And as soon as we can really explain all the breakouts and all the drilling events, so we can say that our geomechanical model is more or less okay. I hope this answers your question.
Okay, sorry, I missed a question. I think I missed a comment. Patrick Kimbatsa said after this presentation, please send us this good presentation file. If can you send it, Mr. Ben Boudiaf, the presentation file?
Yeah, I can send most of those slides. So I will prepare a refined version and send it to you, Sam.
Inshallah. Another questions, Rabia Smida, I'm sorry if I mispronounced your name. What are the application limits in the unconventional reservoirs?
This application limits.
Yes, in the unconventional reservoirs.
So we cannot say that there are limits to the applications of geomechanics, or maybe Mrs. Arbia, you are speaking about all hydraulic fracking related. So I will speak more about challenges that can be overcome. So this, what I have presented, is very basic. So geomechanics, how we're going through the models. But sure, for the unconventional field developments, we are taking into consideration other aspects than only the stresses for the drilling or for the hydraulic fracking. For example, I can mention the very big importance of the mineralogy of the shale into the propagation of hydraulic fractures, instead of only looking at the stresses. I will not say that limits, but those are challenges that can be overcome with the integration of multidisciplinary teams into the work.
Okay, I think Rabia got her answer. Also, Abdul Qadir is asking again, what is the role of geomechanics in enhanced oil recovery? For example, can we consider it for understanding and analyzing thermal production processes?
Can you repeat last part, sorry, for example?
What is the role of geomechanics in enhanced oil recovery?
Yeah.
For example, can we consider it for understanding and analyzing thermal production processes?
Good question. So the role of geomechanics in enhanced oil recovery. So first of all, for enhanced oil recovery, as you know, so we are performing injections. So there are different type of studies that we are performing in order to help in the assessment of those type of projects. One of them is the caprock integrity. For example, if we are doing this thermal recovery, for example, steam injection. So our clients would be interested about the integrity of the caprock, and if it can sustain this injection of steam in the reservoir. This is one kind of application that we are providing. Also, in the enhanced oil recovery within naturally fractured formations. As I mentioned, that the permeability of the fractures is directly related to the geomechanics. So understanding the distribution of permeable fractures such as here. So sorry, I will just go. Understanding the distribution of natural fractures along the reservoir will help into optimizing your injection plan for enhanced oil recovery, either if it's thermal or polymer or anything else. I hope it answers the question.
Thank you so much. Another question by Patrick Kimbatsa.
Okay.
While drilling, what are the different methods to detect the abnormal pressure area, and what's a good one?
Okay, so this should be a question for a mud logger. But so why drilling? So you can you have the different options here. First of all, you can have a look at your cuttings that are coming to surface. So usually when you are drilling over pressurized shale formations, you have presence of splintery and pressure cavings at surface. So those cavings have a very characteristic shape. So they are long and sharp. So sorry, I don't have a picture here like to show to all the audience. So this can be a direct indicator while drilling. So if you are on rig, in order to see if you are like drilling over pressurized. Otherwise, so any kick or something, so it's also a direct like direct indicator. Sorry. So for geomechanics, what we can do as well, so from if we are running LWD, for example, usually in LWD they are measuring resistivity while drilling. They have some measurements while doing like density. So this is kind of application we are doing in several countries in Middle East, Europe, and US. Is that we are constructing a preliminary geomechanical model with a preliminary pore pressure profile. Then during drilling, we are updating the pore pressure profile with the LWD data. So you can, like while drilling, like with very few minutes of the delay, you can detect those over pressurized formations.
Thank you so much. Another questions from Qamardin, not only one. He has too many questions. First, he starts by thanking you. He says, thank you, Mr. Marwan, for this informative presentation. My questions are, while analyzing some stress profiles, have you encountered viscous stress relaxation in a ductile formation, like shales?
Relaxation, so you mean that the shale are sustaining lower stress, right? So yes.
Sorry. He said, if yes, how it's been interpreted? Is it lithology dependent?
It's a very challenging question here because so really, I would say I don't really know because so I can't really answer 100% your question, Qamardin. I really apologize for that. So yes, most likely, so you will have the shale that are sustaining a higher pressure than the sandstone parts. So for example, I think we have met in Hassim Saud during your internship, and you have seen maybe some cases within the very old Cambrian Ordovician where this kind of behavior is reversed. So you have the sandstone that are sustaining higher stresses. So many specialists have tried like you can tell you that many, like every specialist will come up with his own interpretation. So I have discussed with some PhDs on this. So some are pointing the arching effects. Some others saying that's the mineralogy is the main contributor. So I don't think that we have like something that is solid and verified for this. But I will recheck, and so I think we are in contact in LinkedIn, so I can respond you later on if you accept.
Okay, he has also another question. Is there any laboratory creep experiments on these compilant core samples?
Okay, so regarding the creep, so this is a mechanical properties that is not always measured. For example, I think in Algeria, we never done such kind of studies in laboratory. So the creeping, just for the audience, is like for elastic formations when they are deformed under stresses. They have some kind of residual plasticity after coming back to their original form. So maybe drillers and production engineers will know this as thixotropy in fluids. So more or less the same thing. So creping can be useful for analyzing stresses around the salt domes, and also for some kind of shale gas applications. So I don't think that personally, I didn't participate into the similar projects either in Algeria or in Middle East.
Okay, thank you so much. While doing FSP analysis, what is the optimal strike? Fault direction, fault fractures is critically stressed.
Sorry, can you repeat, Osama?
He said, while doing FSP analysis, what is the optimal strike? Like fault direction.
Okay.
Before
This done. Okay, you're speaking about this. So this will depend on your stress distribution, and if so you're going into injection or depletion. So maybe we can discuss this more to details with cases. So there is no like one response to this, I think.
Okay, thank you so much. I want to thank Qamaruddin also for his questions. Thank you so much for attending with us, Qamaruddin. Let me see if there's another question. Yeah, I found another question from Raouf Hashmi. How can geomechanics analysis contribute to the CO2 storage?
Okay. So it is more or less same response as for the EOR. So for CO2 storage, we have done several projects. So mainly are related to the caprock integrity. So this usually for the CCUS. So this is the main concern of all the clients. Is my caprock able to sustain this pressure? So this will be the main application of geomechanics. So we are doing like at the time of actual time, and then so we are doing some sensitivity analysis with Timelapse to see like what is the amount of CO2 that the reservoir can sustain without breaking the caprock. This is like the main application. Second one, so usually so the CO2 storage, so it's not really like not refractory reservoirs are not really like good candidate for CO2 storage applications. But anyway, so the propagation of CO2 through any pre-existing natural fractures can also be inferred by some geomechanical analysis coupled with a dynamic modeling.
Okay, thank you so much. I hope Raouf got his answer. HP, his this name, is asking how can Geomechanics Model help in approaches to net zero, the limit carbon?
This is a very tough question. You should start it with this one.
I went in order.
Okay. So really like as so all like net zero approaches. So also they are linked to the application of like CCUS, geothermal, and everything. So geomechanics is not like a main contributor, but is a part of this puzzle by performing proper analysis that will ensure the smooth operational applications without any risks. So this is really like the purpose of geomechanics, is that ensuring that the things are done safely, either in drilling or in fracking or even in injection. So I'd say that geomechanics is only a part of this puzzle, either for CCUS or geothermal with different kind of applications. So it can help achieving like this net zero by this contribution.
Thank you so much. Anyone can resend the attendance sheet? No. Patrick is asking, when can we perform LOT in the field?
Okay, so LOT is preferably performed after cementing the casing and drilling like a few meters into a new formation. So usually this is when they are performing LOT, and also it serves the geomechanics engineer as so you have the right depth where you are plotting your LOT for calibration. So I have seen some cases like where they are performing it at the end of drilling section. So in order it was more like for drillers, it's for the to design the cement pumping phase, like to not exceed any frac gradient. But if you are performing at the end of the phase with all the open holes, it will be tricky for the geomechanics engineer to plot it. So we don't really know at which depth it is. So we cannot really calibrate properly the model with it. So it's better like to drill 1-2 meters inside new formation and then perform it. This would be the best case for me.
Thank you so much. Moving to another question. What's related between hydraulic fracturing and geomechanic? This question is asked by Adnan Didi.
Okay, so I would say that's the fracture propagation inside the formation. The final geometry of the fracture is driven by the stresses. So this is why we are like analyzing constructing a full geomechanical model prior any frac job. So in order to first, as I said, so geomechanics is aims to conduct like the operations safely. For example, for hydraulic fracking, we can identify what we call the stress barriers that will contain the hydraulic fractures and limit the height of the fracture. So it will ensure the good propagation of the fracture into the formation, and it will also so prevent from the fracture to migrate uncontrollably and to reach any aquifer. So this is why we are doing geomechanics for hydraulic fracking. So in addition to that, like for the horizontal wells, when you are performing multi-stage frac, such as here, so as you can see on this beautiful image with different stages. So the orientation of stresses is very important. So basically, so I will not enter into details, but when you are drilling a horizontal well and you aim to perform a hydraulic fracking to this horizontal well, the azimuth of this well needs to be towards the minimum stress in order to get those transversal fractures. Otherwise, if the well was oriented differently, you will not be able to perform the hydraulic fracking. So this is, for example, a direct application of estimated the direction of the stresses. We also estimate the fracture breakdown pressure from the stresses. So having all the stress and everything, so we can estimate the fracture breakdown pressure. And in the case of naturally fractured reservoir, we can perform a fracture permeability analysis. And so we can calculate at which pressure you will stimulate some natural fractures. For example, here you can see that it's a plot for like fractures that will open with 1000 psi stimulation. For example, all the red spots here means those fractures will be stimulated easily.
Thank you so much. Patrick is asking again.
Okay.
He says that I make so much confusion between FIT and LOT. So what's the difference between them?
Okay. This is a very nice question. I like to answer those questions because I don't like FIT. So usually FIT, so called the formation integrity test. You can also find the FIT called SBT, show bond test, in some with the in some old reports. So usually FIT, what they are doing? They are pumping into at certain pressure. So this pressure will correspond to the mud weight that they will use for the next phase. But they are not going like to initiating any fracture or anything else. So they are just like saying that, for example, they are using 2 SG mud weight for the next phase, means I will pump pressure around 2.05 SG and see if the formation breaks or no. So this is just like something per security only that the drillers are doing. But the FIT cannot be really used to calibrate any SH mean or something, because it can be situated anywhere. It can be situated here, or even here. So we don't know really where is the FIT. It can be at any place. But the LOT, it's the point at which you start seeing this leak off. So it means that you are creating something, some fractures, some asperities that are taking some fluid. This is why you have this slight pressure drop.
Okay. Thanks for answering. Is that all? Mr. Merouane, can you hear me?
Yes.
Yeah, thank you for answering this question. Alauddin Ghorab with another questions. He say, hello, sir. Thank you for this presentation. I kindly ask you about the importance of geomechanics for field engineers and automatic, electrical, and mechanical engineers in the oil and gas industry. Thank you for your answer.
Okay, thank you. So it will depend on where you are working really. For example, for wireline field engineers, so it's mainly like most of them are electrical engineers or automatics that are working in wireline. So basic understanding of geomechanics, not really the stresses, but all the rock behavior related, it can be useful for them. Because, you know, in wireline, for example, you are running tools in open hole. So, for example, you need to understand, like, for example, in some kind of formations, leaving the tool static can be problematic and can cause tool stuck. And usually when in wireline, because it's like a very thin cable, when you have a tool that is stuck, so usually it ends up with a loss in hole, and you have all the problems related to this. So usually, so for field engineers that are working in open hole or everything related with the open hole, either like for frac, it's good to have like a general knowledge of how the rock behave, and for example, that we have something called the frac gradient. We have the pore pressure and how it works. It can be helpful for their daily work.
Thank you so much. I think that was the last question. If anyone has another question, please leave it. We'll wait a bit. Or if anyone want to discuss, please raise your hand so we can unmute you. We'll wait for a few seconds. If not, we will close our meeting. I want to just remind you that this session is sorry, I want to just remind you that this session is an introduction for a training of geomechanics. So who wants to apply for it will have the chance. We'll share the forum next. So stay tuned. I think there will be no other questions. Please, for everyone who is here. Sorry, Ahmed, I should ask a question. Sorry, Ahmed. Can you tell us the difference between fast formation and slow formation, please?
Fast and slow formation. Okay. So it will depend on your applications here, Imad. So usually what we call fast formations is so it's related to the acoustic slowness here. So what you can also, so you know it as DTC or DT. So is the compressional acoustic slowness of the rock. So usually, for example, for sandstone with some porosity, the acoustic slowness is around 60 microsecond per foot. For shale, it can go even higher than 150, for example, here on the top section. So slow formations. So usually it's so for the open hole. Okay, I will go for the case hole after that. For the open hole slow formations, usually is when you have the compressional and shear slowness very high, and for sometimes the shear slowness cannot even be like measured properly by the tool, so it needs advanced processing by a geoscientist to be constructed. So this is what we call slow formations, and usually those slow formations are either shale or unconsolidated sandstone. For the fast formations, usually it's very compacted formations or carbonates, because the sound propagates very fast in carbonates, even if they have high porosity. So it can go down to 45 microsecond per foot, for example. For anhydrite, it's even like for very compact anhydrite, it can go even lower than that. So those are called fast formations. So this is related to the open hole. For the cased hole, so this term is used in cement evaluation. So when you are interpreting your VDL or CBL, presence of fast formations needs to be known before to start interpreting, because, for example, if you have anhydrite, okay, we'll not enter into too much. Maybe for people that have experience in this, into seeing a VDL, but you have your casing arrivals before, and then you have the formation arrivals. Fast formations is when the formation arrivals arrive before the casing. This happens when you have anhydrites usually. So these are so can be tricky when you are interpreting your cement bond log, but it's okay. So as soon as you have the information, it's simple to get through it. I hope it answers your question.
Thank you so much. Thank you so much. I hope too he got his answer. Patrick is asking again, can we have this good presentation?
Yeah, no problem. I will send you a PDF version.
Okay, inshallah, I hope. Alauddin Ghorab, he's saying, thank you so much, sir. These webinars are like an introduction and general information for me as an automatic engineer, graduate student, so that I can be aware about anything in the oil and gas industry in my future internship and further job positions in my career. Thank you again. Thank you to Alauddin.
Thank you, Alauddin. Nice words. Thank you.
Ahmed is also thanking you. I want to remind you again to fill the attendance sheet and know that this webinar is an introduction for a training of geomechanics. Those who want to apply, stay tuned with our social media pages. Mr. Ben Boudiaf, I can't thank you enough. Any appreciation statements would be enough to thank you. Thanks for your job. Thanks for this amazing presentation. Thanks for your explanation. It was perfect. Thanks for your energy. I hope we can meet you again in our future events. Thank you so much.
You're most welcome, Osama. I would like to thank SP Boumerdes Student Chapter for organizing this event and for the very nice work you are doing. So you are doing really an amazing work, and I'm really proud. As previous Boumerdes student, I'm really proud to see this energy in you guys. So thank you for this, and also thanks to all the attendees for today and for the very nice questions and discussion. And so yes, looking forward for future events, inshallah.
Thank you so much, Mr. Ben Boudiaf. I hope you enjoyed the time with us too.
Yes, about